Hello, today I'll be presenting a systems level look at how granite mining impacts the carbon and nitrogen cycles. We'll explore the flow of environmental changes caused by mining, the interactions between components, and how feedback loops either amplify or reduce these effects over time. First, allow me to introduce the table and graphics I will be using to explain the role granite mining plays in the carbon and nitrogen cycles. Excuse me. This first is a table summary that has the components, the boxes, and the roles these components play in the system. The first box is granite rock formation, which is a source material for mining, followed by the second box, granite mining operations, which disrupts land and ecosystems. Third box is soil disturbance, which alters microbial balances and leads to erosion. The fourth box is vegetation removal, which eliminates carbon sinks. The fifth box is carbon storage and vegetation, which is carbon held in plant biomass. The sixth box is microbial activity in soil, which is essential for nutrient cycling and decomposition. The seventh box is nitrogen fixation, which is key nitrogen inputs to soil erosion. The eighth box is reduced soil fertility, which impairs regrowth and ecosystem function. The ninth box is water pollution, or nitrates, which degrades aquatic systems. The 10th box is land reclamation or rehabilitation, which is an attempt to restore ecosystem and soil health. The 11th box is carbon sequestration, or which is post-mining. And that is the reabsorption of carbon dioxide via new vegetation. The 12th box is the 12th box is land reclamation, which is the same as the 10th box, land reclamation. And the 13th box is atmospheric carbon dioxide, which is increased from loss of vegetation and organic carbon. Now, let's begin with the key components in the system, organized in a flowchart with 13 elements. These include environmental structures like granite rock and soil, biological processes such as microbial activity and nitrogen fixation, and human interventions like mining and reclamation. The left side of the diagram is the carbon cycle side. Granite rock formation goes to granite mining operations. And as more granite is available, mining activity increases. This is a positive coupling. Granite mining operations then go to soil disturbance. Mining physically disrupts the soil, increasing soil disturbances. Granite mining operations also go to vegetation removal. Mining typically involves clearing vegetation, reducing plant cover. Vegetation removal goes to carbon storage and vegetation. When vegetation is removed, less carbon is stored in plant biomass. This is a negative coupling. Carbon storage and vegetation goes to atmospheric carbon dioxide. A reduction in carbon storage again means more carbon remains in the atmosphere. Again, a negative effect. The right side of the diagram is the nitrogen cycle side. Soil disturbance leads to microbial activity in the soil. Disturbance damages soil microbes, reducing their activity. Microbial activity in soil leads to organic matter decomposition. Healthy microbes speed up decomposition, which releases nutrients. Microbial activity in soil leads to nitrogen fixation. Microbial health also supports nitrogen fixation, a key process for replenishing soil nitrogen. Soil disturbance also leads to nitrogen fixation, which directly disturbance harms the nitrogen fixation process. Soil disturbance leads to soil erosion, as loose, disrupted soils can erode more easily, and this soil erosion leads to runoff in water bodies. This eroded material enters nearby rivers and lakes, which then leads to water pollution of nitrates. That runoff often contains nitrogen compounds, contributing to water pollution. Nitrogen fixation also leads to increased soil fertility. Reduced soil fertility leads to further nitrate water pollution. To compensate for poor soil, people may overuse fertilizers, worsening nitrate runoff. The bottom of the diagram is the reclamation side. Land reclamation and rehabilitation leads to carbon sequestration, which is post-mining. Efforts to restore the land lead to regrowing vegetation and resequestering of carbon. Carbon sequestration leads to atmospheric carbon dioxide. More carbon stored in vegetation means less carbon dioxide in the air. Reclamation leads to microbial activity in the soil. Healthy soils support microbial recovery. And microbial activity leads to nitrogen fixation, which again enhances nitrogen cycling. On the screen, you'll see the flowchart that maps these 13 components and their interactions. Each arrow represents a coupling, positive or negative, and the direction of influence. You can also see how two cycles intersect via soil health and microbial activity. Let's take a look at a stabilizing loop that helps the system recover, which is also known as a negative feedback loop. Land reclamation leads to carbon sequestration. Carbon sequestration leads to atmospheric carbon dioxide, and atmospheric carbon dioxide mitigates climate impact and facilitates more effective reclamation. This feedback loop shows how human intervention can begin to reverse damage over time. An amplifying loop that can lead to environmental degradation is also known as a positive feedback loop, and positive feedback loops are destabilizing. Granite mining leads to vegetation removal, which leads to increased carbon dioxide and climate stress, I'm sorry. Climate stress makes it harder for vegetation to regrow and slows reclamation efforts. Slower reclamation efforts lead to sustained high atmospheric CO2. This is an example of how a system can spiral if impacts go unchecked. In conclusion, granite mining impacts both the carbon and nitrogen cycles through vegetation loss, soil disruption, and water pollution. However, with careful reclamation and soil restoration, these effects can be partially reversed. Understanding these systems help us design more sustainable approaches to resource extraction.